Hey all, so we are proving this question of using induction. I have to prove that 2 times the summation of I going from 2 all the way up to n minus 1, 3 to the power I is equal to 3n minus 1. And the base case, there is a hint right there for you. The n starts at 3. So even though the summation starts at 2 here, but the equation where what you see in front of you, which is the left hand side equals the right hand side, only holds when n is greater than or equal to 3. So we'll start with the first step of our principle of mathematical induction, which is write down your statement. P of n, it's a predicate function, so I'm going to copy the left hand side, which is summation going from 2 I going from 2 all the way up to n minus 1, 3i. I'm just copying down the question again. Okay, so that's just the statement. Now the base case is the second step. Technically, what you do is base case. You start with the starting element of your domain. In this case, all integers n greater than or equal to 3. So I'm gonna take n equals 3 as the base case. In other words, that means P of 3. So for P of 3, I want to prove that left hand side equals right hand side. So I have to calculate the left hand side first. Left hand side, and let's just, put a divider here. So put n equals 3. Now be careful. This is another mistake that I see a lot is, another mistake that I see a lot is this is a summation, okay? You are plugging your n in the summation. So do not get rid of the summation. So what is going to happen here, you'll do 2 times summation I going from 2, and then we have n equals 3. So in place of n in the left hand side, I'll put 3. Okay? And on the right hand side is just a simple equation, which is just 3 to the power 3 minus n, minus 9, right? So I'm just plugging in n equals 3, both sides, and see what we get in the right hand side. So 3 times 3 is 9, times 3 is 27. 27 minus 9 is 18. Okay, so let's simplify this side. Well, this is just 2 times summation I going from 2 to 2, right? 3 to the power I. Well, that's just one term, which is plug I as 2. So I've got 2 times 9, which is 18. And that's what we want. If I give you a proof by mathematical induction, I have a base case and all that stuff. The starting case should work out unless you've done something wrong. So in this case, P3 is true. Okay, then we go back to the inductive step. The inductive step, and these steps will stay common for every proof question that you'll see. Inductive step is I need to assume that Pn is true for arbitrary integer n where n is greater than or equal to 3. So I'm gonna assume that this is true. So I'm just gonna write the equation that I'm assuming is gonna hold. So 2 times summation I going from 2 all the way up to n minus 1, because that's my Pn if you see above. I'm just assuming the question is true for an arbitrary equation. We will call this equation 1. Okay, don't forget this, the 1, equation 1, because you have to use this equation. Now it looks like I'm going to run out of space here. which is very common with me. So to prove, of course, nothing works. To prove P of n plus 1 is true, right? So I have to prove Pn plus 1 is true. That is, it's useful to write it out explicitly what we need to prove, especially under exam pressure, right? It's useful to write it out. So to prove Pn plus 1, so I'm looking at equation 1. I'm going to replace everywhere you see n, replace it with n plus 1. And that equation is what we need to show, that LHS equals RHS and all the do process. So I'm going to replace n with n plus 1. So the left hand side will become 2 summation I going from 2 all the way up to. So n plus 1 minus 1 is just giving me n. Okay. And I have to prove that this is equal to 3n plus 1 minus 9. Let me just say that this is something we need to prove. We need to prove. You can't assume this. Need to prove LHS equals RHS. Now, once you have proved this, then the question is done, right? So how do I go about proving it? Now, I'll try to fit whatever I can in this question, in this area. Then otherwise, I'll move to the next. I'll need to open a new document. So, of course, I'm going to start with the left-hand side. I see a summation. I will break up that summation into two parts, right? Because that's the first thing you should do if you see a summation, and you must use equation 1 somewhere in your proof. It must be used, otherwise you're doing something wrong. So I'm gonna consider left hand side. So I'm considering left hand side. I'm gonna break that summation up. So this will be 2 summation I going from 2 all the way up to n minus 1, 3 to the power I. I go to the second last term. And why am I doing it? Because I already am given something in the inductive step. I'm getting closer to this part, right? Because then I can replace it with the right hand side of equation 1, because that's something we must use. So I'm gonna break this up. So the last entry of this sum will be, because the 2 distributes, right? So 2 distributes to the last entry, which is 3 to the power n. Make sense? Now I know that this is equal to 2 times 3n minus 9 plus 2 times 3 to the power n. I don't know how this happened. I can't even. How do I go back? Control Z. Alrighty. So, sorry, I have a strike through here. I didn't do it. I don't know how it happened. So, now how we go from here? Because I need 3n plus 1 minus 9, right? Let me open a new document. I need to fix this proof. Once I post the notes, this will be looking nice. Okay, now I need to explain this anyways to you guys. Remember what was 1? 1 was 2 summation I going from 2 all the way up to n minus 1, 3I equals 3n minus 9. This was equation 1, okay? We had to prove Pn plus 1, which is 2 times summation I going from 2, because I'm replacing n with n plus 1, I get n here. 3I equals 3, replacing n with n plus 1, I get this. Right? And this is what we need to prove, that LHS equals RHS. So I considered the left hand side. I started with the LHS and I broke up, just like you have this I going from 1 to 100, say, okay, 3I. you are breaking this summation up. This is what I mean. I'm gonna go all the way up to the second last entry, and then I'm gonna add the last entry, which is just 100. Make sense? So I broke this summation up. Now this is not a part of the question. This is just me explaining how I'm breaking this summation up. Now why am I breaking this summation up? Because I have something, an easy form for this up to the second last term, and I have to use my assumption. So I break this up. The 2 goes with both summations. Summation going from I equals 2 up to n minus 1, 3i, and then I'm gonna add 2 times. So what is the last term? Last term is n, so I becomes n, right? And the right hand side is something we need to prove. But I can use 1 here. I can use 1 here and replace this summation, actually replace the whole thing, because 2 times the summation is 3n minus 1. So I got 3n minus 9 plus 2 times 3n. But it doesn't look like I need to get 3n plus 1, right? So add this, what do you get? 2 plus 1 times 3n is 3 times 3n minus 9, which is 3 to the power n plus 1 minus 9, and which is exactly RHS, right? And this is the good amount of work that I need you to show in your proof. Like you must prove explicitly that LHS equals RHS. You cannot assume things, you have to prove it. And once you're done proving it, then there's a closing statement. Therefore, by principle of mathematical induction, copy the question again. Copy the question. Okay, I won't even bother writing the statement. So this was one proof, and then I'm just going to give you a hint. Try it yourself. Maybe I'll give this to you in a quiz one day. Okay, no, this is not the proof. This is the one. Wait, I thought I had one more proof that I wanted to just give you the hint a little bit. Use induction to prove that n factorial is, sorry, the question is, because I have notes, I want you to focus on this question, example number 9. Use induction to prove that n factorial is greater than 2n for all integers n greater than or equal to 4. Now, of course, the full solution will be in my lecture notes. I just want to give you an starting point on how to write this proof. What is n factorial? Starts with n times n minus 1, n minus 2, all the way up to 1. What is the statement? Pn is n factorial. There is no equal to. Why do I write? This bad habit of writing equal to. Greater than 2 to the power n for n greater than or equal to 4. Okay, base case. What is base case? Well, do n equals 4. So we are looking for P4. What is 4 factorial? The left hand side is 4 factorial, which is 4 times 3 times 2, which is 12 times 2, 24. What is the right hand side? The right hand side is 2 to the power 4. Right? So this is 2 times 2 times 2 times 2, which is 16. Well, clearly 24 is greater than 16. So P4 is true. And so that you can just go about this proof. Think about it. I'm just gonna write down the inductive step. Inductive step. We assume Pn is true for, you see the process is very similar for each question. You prove your base step, and then you prove your assume your inductive step. Assume Pn is true for arbitrary integer n, where n is greater than or equal to 4. So I'm gonna write down the equation, or in this case inequality, and call this 1. We have to prove P of n plus 1 is true. That is, what is it asking you to prove? That is, n plus 1 factorial is greater than 2 to the power n plus 1. Now you must ask, like, how do I get this proof? Because I need to use equation number one. Equation number one that I just, highlighted here. The assumption, the inductive hypothesis must be used somewhere. Go back to the definition of induction. Sorry, go back to the definition of factorial. What will you get? You'll get n plus 1 times n factorial, right? I'm just taking the left hand side of this inequality that I need to prove. Because what is n plus 1 factorial? Let me go back here. What is, this is just background information. What is 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1, right? Which is in other words 5 times 4 factorial. What is 10 factorial? 10 factorial is 10 times 9 times 8 and so on, which is 10 times 9 factorial in other words. So what is n plus 1 factorial? Which is n plus 1, and we need to be comfortable with these playing around with factorials, because it's extremely important when we learn about combinatorics. So be comfortable with playing with the factorials and stuff like this, and ask me if you have any questions. So I have n plus 1 times n factorial, but what do I know about n factorial? I know that this is gonna be, I just wrote it like this. I'm just gonna make sure we understand this, right? N plus 1 factorial is equal to this. And I know that this is gonna be greater than n plus 1 factorial, n plus 1 times 2 to the power n, right? Now I know for a fact that n is greater than or equal to 4, right? So this n is positive and it's greater than or equal to 4. So if I replace it with 1, it will still work, right? Because n is 4 or more. So I'm just replacing it with 1. Definitely going to be bigger. So I just proved that this is 2 times 2 to the power n, which is nothing but 2 to the power n plus 1. So I proved that n plus 1 factorial is greater than 2 to the power n plus 1. And this is exactly what I needed to prove, because I know that n is greater than or equal to 4. That's the assumption. We assume that the proof only holds for n greater than or equal to 4. So I can replace n with 1 and it will definitely be greater than that, right? Like for example, you know that y is greater than 4. Can I say that y is greater than 1? Obviously, right? Because we know that this is true, so this must be true. So I know that n is greater than 4, so it has to be greater than 1. That's the kind of manipulation that we're using here. And of course, then you do the, therefore, Pn plus 1 is true, right? Hence, by principle of mathematical induction, copy the question again. So this is it. These two proofs conclude the syllabus that is covered for exam 3.